Hi kids, this is video 21. This talks about Newton's third law, and the essential question is, how do forces fit into our understanding of the conservation principles? So how does this all wrap up in conservation, which is really sort of the big laws that underlie physics? I'm going to revisit the definition we made of force a little bit ago, because there's something important in it that we didn't really talk about. We said that a force is a single interaction or contact between two objects, but so far we've only been focusing on the forces acting on one of those objects. We've been defining which other object was pushing or pulling, but we haven't really been talking about what's happening to that other object. So the idea is that we've already learned that it's a single interaction. Newton's third law basically says that since it's a single interaction, the amount of force each object is experiencing in that interaction is the same, and that they are pushed or pulled in opposite directions. So if I push on you, you experience a force in one direction, I experience a force from you in the other direction, and those forces are also going to be the same amount. This idea is where conservation of momentum and actually conservation of energy are derived from originally. Every single force in the universe will actually be changing the momentum and energy of both objects that are in the interaction at the same time by the same amount in opposite directions. And this is how we keep energy and momentum in the universe conserved. So an example, right, we got two people touching each other. That person on the left experiences a force from the person on the right. I guess I called the person on the left A and the one on the right B. And the person on the right experiences the same force from A on them in the opposite direction. In other words, there's no way to touch someone or something else without them also touching you. And the harder you touch them, the harder they're going to touch you back. So this is actually a pretty challenging idea. So I want to go through a couple examples of where we can see this equal and opposite force in other applications. We did a lot of momentum examples where we had things like ice skaters pushing off of each other. So we actually, can you apply Newton's third law in this situation? We know that they're both going to change momentum the same amount, but now we also know they're both going to be experiencing the same force in opposite directions. In other words, it doesn't really matter which of these two ice skaters is doing the pushing. They're both going to be experiencing the same amount of force either way. One is pushed to the left and the other is pushed to the right so that we can keep momentum in our universe conserved. An example that's a little bit harder to picture is an apple falling off a tree towards the earth. The force that's causing it to accelerate is the force of gravity from the earth. And Newton's third law says that that means that the earth has to be experiencing an equal and opposite force of gravity upwards from the apple. And so that is hard to see because the earth is entirely huge compared to the apple. And we can't see the apple, we can see the apple's momentum changing, but we can't see the earth's momentum changing because it's so big. One more example has to do with a person pushing the piano along the ground. So let's say this is a rough ground. We could do a free body diagram of this piano. I'm gonna draw the forces on here, although I'm not gonna turn it into a free body diagram. But hopefully you could identify that there's four forces acting on the piano. Number one, force of gravity acting on the piano by the earth. Number two, a normal force acting on the piano from the ground. Number three, a normal force acting on the piano from the pusher to the right. And number four is a force of friction on the piano provided by the floor surface. So these are all the forces on the free body diagram. Newton's third law says that each of these forces is actually a pair of forces, one on the piano and one on the other object that is involved in the interaction. So that gravity force on the piano by earth means that there must be another force of gravity on the earth by the piano in an opposite direction and the same size as the force on the piano. There also has to be another normal force on the ground by the piano. You can probably picture this, right? The piano is pushed up by the ground, but the piano is going to be pushing downwards on the ground, making little dents in the ground, if you can imagine that. There is a normal force on the piano from that pusher. And there's also a force on the pusher by the piano, right? Their hands might hurt eventually because they are being pushed on by the piano backwards. And then the last thing is that there was friction on the floor, or on the piano by the floor, and there's also going to be friction on the floor by the piano. So the floor is going to be pushed forwards a little bit by the piano as it's sliding. A couple summaries here. In each of these pairs of forces that have the same color, one force is on the piano, which belongs on the free body diagram, and the other is on the other object. It wouldn't be on the same free body diagram because it would be on a free body diagram of the other object that is involved. Both of the forces in a pair are the same kind of force. So we're always going to have pairs that are both gravity or both normal or both friction. You'd never have a pair of forces where one was one type and the other was the other because they're a single interaction. Also, both forces in a pair are equal in size, right? You notice that in the drawing that I made, the normal force is a big one. We're pushing really hard. Friction is small, and they're the same size. Both of those friction forces are the same size, even though they're on different objects. And then the last thing is that the paired forces are in opposite directions. So one of the gravity forces is down, the other is up. One of the normal forces is down, the other is up, etc. So how do we get back to conservation? Well, let's do another classic example of like my two objects pushing off each other. We did that a lot in momentum, but this time I'm going to have a big object and a little object, and I think we already know when they push off each other, they're going to go in opposite directions, and the big one should go slowly and the little one should go fast because that's how we can keep momentum in that system conserved. This is that explosion situation. But we also know that they experience the same amount of force, right? So the big one experiences a normal force from the push to the left, the little one experiences a force to the right. Even though the little one goes flying, it's experiencing the same amount of force as the big one that doesn't move as much. The time in this interaction is the same. In other words, while they're touching each other, the green one is touching the blue one for the exact same amount of time the blue one is touching the green one. You can't touch somebody for more or less time than they're touching you back because it's a fundamental to the interaction. One thing that's different is the masses, right? That green one has a big mass, the little one has a small mass, and as we probably already know from momentum, they're going to have different changes in velocity. In this interaction, the green one is going to have a much smaller change in velocity than the blue one does. If we made a more or less same table for this with those four variables, you would see that green and blue guy both have the same force because of Newton's third law, the same amount of time in contact, and one has more force or more mass and less velocity change, and the other one has less mass and more change in velocity. We can really see this brought back to conservation when you go back to that equation that we've used several times. I'm going to rearrange it slightly so it looks like this. I multiplied T and M on both sides, so I ended up with this sigma F delta T equals M delta V. And the reason that I did that is because the left side of that equation basically has the Newton's third law stuff in it. It's showing that they both have the same force and they both have the same amount of time in contact. Those two variables are the same for both objects in the interaction. But the right side of the equation, M delta V, is change in momentum. And so M times V is momentum, so M delta V is how much momentum is changing. And it basically shows me that for any given interaction, for any force between two objects, each of those objects is going to have the same mass times the change in velocity. So if one has a big mass, the other one will have a bigger change in velocity so that we can keep momentum conserved in the system. Okay, please take a few minutes to revisit the essential question, how do forces fit into our understanding of the conservation principles? Thanks for watching.